Hello and welcome to Module 1 of Biopsychology. I am your professor, Dr. Horowitz, also affectionately known as Dr. B. Now, instead of going over all the chapters, the first one is pretty self-explanatory, pretty easy to go through on your own with the ideas of the history of how biopsychology came around and the ideas of genetics and nature versus nurture. However, if you do have questions about the complexity of genes or understanding the slides on which thumb goes over which one when you clasp your hands, I will be more than happy to elaborate as long as you ask me. Today I really wanted to concentrate on Chapter 2, which talks about the action potential and the neurons and neural communication, and I just wanted to give a quick overview. The parts of the neuron are pretty easy. You learn them in Psych 1, and sort of the insight into the action potential. But this one goes a little farther into the actual components of the action potential, and so I thought I would explain it, and hopefully you could sort of understand a little better. So you knew from intro psychology that the sort of action potential, the way that it flows is that something comes in, it causes a spike, or it hits the threshold, it spikes, and it's an all or none phenomenon. So I wanted to sort of get into the idea of where this comes from. So we talk about membranes at rest being at about negative 70 millivolts. And the reason why it's negative 70 is because we take the measurement of how many volts inside versus outside of the cell, and we basically do the math. And it is 70 millivolts less inside the cell. Now, why is this? Outside the cell, there are mostly positive ions in the form of sodium, and that keeps it around zero. The reason that even though there are positive ions, potassium, inside the cell, there are also a lot of huge negative, what we call anions, inside the cell. And so it is more negative on the inside of the cell because of these anions, because of these negative ions, than it is outside the cell, which is mostly sodium. So that's why at resting potential, when nothing is going on, the cell is at negative 70 or so. Now, what happens is the voltage changes, which causes the action potential. Now, why does the voltage change? Well, maybe a drug or something opens a receptor and it causes what we call depolarization or hyperpolarization, depending on if the ions are positive or negative. If you're at negative 70, positive ions are going to depolarize and move you closer to zero, and negative ions, such as chloride, would cause it to be more negative, right? So that would be called hyperpolarization. So let's also understand the forces that are at work here. And if you follow along, this I believe is slide 13 on chapter 2. The two forces that cause ions to move across the membrane to change the voltage in a neuron are diffusion, which just means that the force wants to be from a higher concentration into a lower concentration, and the other one is called electrostatic pressure. So if it is negative inside the cell, then the cell wants to be more positive. It wants to go away, kind of like a magnet where opposites attract. Negative likes positive, positive likes negative. So let's first concentrate on diffusion. Sodium is concentrated outside of the cell. It's kind of like being in line for a club and it being really crowded, and all you want to do is get inside. Or, if you're potassium inside the cell, it's like being in a crowded house party And what do you want to do? You want to go get some fresh air outside where you can sort of relax and stretch. So sodium wants to come into the cell and depolarize it because it is highly concentrated outside the cell, so diffusion, and it is also negative inside the cell, so positive sodium wants to go into a more negative environment. So both diffusion and electrostatic pressure are calling it, so to speak, forcing sodium to want to come in. When that cell hits and depolarizes enough sodium comes through, it goes from -70 to maybe -65, wherever that threshold is, usually around -65. Once that happens and it hits the threshold, it opens every sodium channel so that sodium kind of jailbreaks into the cell. And that's where you get the spike for the action potential to begin. If you hit the threshold and depolarize it enough, it opens all the sodium channels, and that big spike is the sodium channels coming through and depolarizing the cell. So the cell depolarizes so much because all the sodium channels open, it causes that huge spike that goes past 0 and all the way up to about positive 30 millivolts. At the top of that spike, all the sodium channels inactivate and close, so no more sodium is allowed to enter the cell. At this point, the cell is now positive, up near positive 30, as opposed to where it was before at -70. So here's potassium. Potassium's story is that it's highly concentrated inside the cell, so potassium now wants to be outside and not in the crowded house party. So potassium wants to leave the cell. Also, because it's now more positive in the cell than it is outside, electrostatic pressure says that potassium wants to go out because of diffusion and because it wants to be in a more negative environment. So the downside, or downswing, of the action potential after the spike is the fact that sodium's no longer allowed to enter, and potassium is doing the only thing. It's leaving the cell. So I just told you that sodium channels open and close very rapidly. Well, potassium channels are kind of like our garage doors. They close kind of slow. So what you'll see in the action potential chart is that after the spike that goes up to about positive 30, you see it go down, and then as soon as it goes back to resting potential of -70 to return back to normal, the potassium channels then start to close. And it is only at this point that they close slowly, so it actually overshoots resting potential and goes down to about -80 before it comes back to normal at -70, and the sodium channels are reset. So I just wanted to give you a little bit of information on exactly what it is and how it is that these ions move and cause the change in voltage that allows the action potential to come down the axon. And once the action potential activates, again, it's an all or none phenomenon, so if you reach threshold, you will 100% every time, the all part, have an action potential. What the action potential does is it causes the calcium to come in at the terminal button, and that calcium that is basically a messenger from the action potential signals the neurotransmitter to bind to the end of the synaptic terminal or the terminal button, and there it can be released into the synapse for the postsynaptic cell to take it up. So even though the actual communication between neurons is chemical, it is this electrical action potential ion movement that allows this electrical signal that allows the chemical to then fuse to the end of the synaptic terminal and be released. And then it's picked up by the other cell. If it is positive, right, it'll cause a depolarization on the other side. If it's negative, it will cause a hyperpolarization. I hope you've enjoyed this little intro, and any questions, please contact me.